right, this is CS50, and this is the start of week 2. So let us begin today with a bug. A bug, of course, is a mistake in a program, and you'll get very familiar with this concept if you've never programmed before p set 0 and now p set 1. But let's consider something a little simple at first. This program here that I threw together in advance, and I claim that this should print 10 stars on the screen using printf, but it's apparently buggy in some way. Given that specification, that it should print 10 stars, but it doesn't apparently, what would you claim is the bug? Yeah. So it's an off by 1 error, and what do you mean by that?
When you're building loops, the index that you start at is very important, and
Okay.
also the boundary on the number. So for example, you have less than or equal to, whereas if you changed it to just less than, that can fix it.
Excellent. So we've specified a start value of 0 for I, and we've specified an end value of 10, but we've used less than or equal to. And the reason that this is 2 characters and not just 1 symbol like in a math book is because you don't have a way of expressing the 1 character equivalent. So that means less than, but if you start counting at 0, but you count all the way up through and equal to 10, you're of course going to count 11 things in total, and so you're going to print 11 stars. So what might be a fix for this? Yeah. So just adjust the less than or equal to just be less than. And there's, I claim, perhaps another solution too. What might else you do? Yeah. So to start equaling it to 1 and leave the less than or equal to. And frankly, I would claim that for a typical human, this is probably more straightforward. Start counting at 1 and count up through 10. Essentially do what you mean. But the reality is in programming, as we've seen, computer scientists and programmers generally do start counting at 0. And so that's fine once you get used to it. Your condition will generally be something like less than. So simply a logical error that we could now fix and ultimately recompile this and get just 10. Well, how about this bug here? Here again, I claim that I have a goal of printing 10 stars, 1 per line this time, but it doesn't. And before we propose what the fix is, what does this print visually? If I were to compile and run this program, do you think? Yeah. Stars, so all the stars on the same line is what I heard, and then the new line character. So let's try that. So make buggy-1, enter, and I see the clang command that we talked about last time, /buggy1, and indeed I see all 10 stars on the same line, even though I claimed in my specification, just the comments atop the code, that I intended to do 1 per line. But this looks right. Right, on line 15, it looks like I'm printing a star, and then on line 16, it looks like I'm printing a new line character, and they're both indented, so I'm inside of the loop clearly. So shouldn't I be doing star, new line, star, new line, star, new line? Yeah. Yeah, unlike a language like Python, if you're familiar, indentation doesn't matter to the computer. It only matters to the human. So whereas here I've indented lines 15 and 16, that looks beautiful, but the computer doesn't care. The computer cares about actually having curly braces around these lines of code so that it's clear, just like in Scratch, that those 2 lines of code should be executed, like one of those yellow Scratch puzzle pieces, again and again and again. So now if I rerun this program, /buggy2, I have an error now. What did I forget to do? Yeah, so I didn't compile it. So make buggy2, no such file because I didn't actually compile the second version. So now, interesting, undeclared variable, oh, wrong, not 2, we're doing 1. Make buggy1, /buggy1, and now each of them is on the same line. Now, there is an exception to this supposed claim of mine that you need these curly braces. When is it actually okay, if you've noticed in section or textbooks, to omit the curly braces? Yeah. Exactly. When there's only 1 line of code that you want to be associated with the loop, as in our first example, it is perfectly legitimate to omit the curly braces just as sort of a convenience from the compiler to you. Yeah?
Would it be considered a style error?
Good question. Would it be considered a style error? We would promote, as in CS50 style guide, the URL for which is in pset 1, that always use the curly braces. Certainly if you're new to programming, the reality is we're not going to prohibits you from doing these conveniences. But if you're just getting to the swing of things, absolutely just always use the curly braces until you get the hang of it. Good question. All right, so that then was a bug, at least in something fairly simple, and yet you might think this is fairly rudimentary, right? This is sort of the first week of looking at a language like C or bugs therein, but the reality is these are actually representative of some pretty frightening problems that can arise in the real world. So some of you might recall, if you follow tech news or maybe even caught wind of this in February of this past year, that Apple had made a bit of a mistake in both iOS, the operating system on their phones, and also macOS, the operating system on their desktops and laptops. And you saw such headlines as this. And thereafter, Apple promised to fix this bug, and very quickly did fix it in iOS, but then ultimately fixed it in Mac OS as well. Now, none of these headlines alone really reveal what the underlying problem was, but the bug ultimately reduced to a bug in SSL, Secure Sockets Layer. And long story short, this is the software that our browsers and other software use to do what? If I said that SSL is involved whenever you visit a URL that starts with HTTPS, what then might SSL be related to? Encryption. So we'll talk about this in the coming days, encryption, the art of scrambling information. But long story short, Apple some time ago had made a mistake in their implementation of SSL, the software that ultimately implements URLs like HTTPS or MAC's connections there too, the result of which is that your connections could potentially be intercepted. And your connections were not necessarily, in fact, encrypted if you had some bad guy in between you and the destination website who knew how to take advantage of this. Now, Apple ultimately posted a fix for this finally, and the description of their fix was this: secure transport failed to validate the authenticity of the connection. The issue was addressed by restoring missing validation steps. So this is a very hand-wavy explanation for simply saying that we screwed up. There was literally one line of code that was buggy in their implementation of SSL, and if you go online and search for this, you can actually find the original source code. For instance, this is a screenshot of just a portion of a fairly large file, but this is a function apparently called SSL verify sign server key exchange, and it takes a bunch of arguments and inputs, and we're not going to focus too much on the minutia there, but if you focus on the code inside of that topmost function, let's zoom in on that, you might already suspect what the error might be, even if you have no idea ultimately what you're looking at. There's kind of an anomaly here, which is what? Yeah, I don't really like the look of two go-to fails. Frankly, I don't really know what go-to fail means, but having two of them back to back, that just kind of rubs me intellectually the wrong way. And indeed, if we zoom in on just those lines, this is C. So a lot of Apple's code is itself written in C, and this apparently is really equivalent, not to that pretty indentation version, but if you recognize the fact that there's no curly braces, what Apple really wrote was code that looked like this. So I've zoomed out, and I've just fixed the indentation in the sense that if there's no curly braces, that second go-to fail that's in yellow is going to execute no matter what. It's not associated with the if condition above it. So even again, if you don't quite understand what this could possibly be doing, know that each of these conditions, each of these lines, is a very important step in the process of checking if your data is in fact encrypted. So skipping one of these steps, not the best idea. But because we have this second go-to fail in yellow, and because once we sort of aesthetically move it to the left where it logically is at the moment, what does this mean for the line of code below that second go-to fail, would you think? It's always going to be skipped. So go-tos are generally frowned upon for reasons we won't really go into. And indeed, in CS50, we tend not to teach this statement go-to. But you can think of go-to fail as meaning go jump to some other part of the code. In other words, jump over this last line altogether. And so the result of this stupid, simple mistake that was just the result of probably someone copying and pasting one too many times was that the entire security of iOS and macOS was vulnerable to interception by bad guys for quite some time until Apple finally fixed this. Now, if some of you are actually running old versions of iOS or macOS, you can go to gotofail.com, which is a website that someone set up to essentially determine programmatically if your computer is still vulnerable. And frankly, if it is, it's probably a good idea to update your phone or your Mac at this point. But there, just testament to just how an appreciation of these lower level details and fairly simple ideas can really translate into decisions and problems that affected, in this case, millions of people. Now, a word on administration. Sections. We'll start this coming Sunday. You will receive an email by the weekend about section, at which point the resectioning process will begin if you've realized you now have some new conflicts. So this happens every year, and we will accommodate in the days to come. Office hours, do keep an eye on this schedule here. Changes a little bit this week, particularly the start time and the location, so do consult that before heading to office hours any of the next 4 nights. And now a word on assessment, particularly as you dive into problem sets 1 and beyond. So per the specification, these are generally the axes along which we evaluate your work. Scope refers to what extent your code implements the features required by our specification. In other words, how much of a piece set did you bite off? Did you do a third of it, a half of it, 100% of it? Even if it's not correct, how much did you attempt? So that captures the level of effort and the amount to which you bit off the problem set's problems. Correctness, this one, to what extent is your code consistent with our specifications and free of bugs? So does it work correctly? If we give it some input, does it give us the output that we expect? Design. Now, this is the first of the particularly qualitative ones, or the ones that require human judgment. And indeed, this is why we have a staff of so many teaching fellows and course assistants. To what extent is your code written well? And again, this is a very qualitative assessment that we'll work with you on bidirectionally in the weeks to come, so that when you get not only numeric scores, but also written scores, or typed feedback, or written feedback in English words, that's what we'll use to drive you toward actually writing better code. And in lecture and sections, we'll try to point out as often as we can what makes a program not only correct and functionally good, but also well designed, the most efficient it can be, or even the most beautiful it can be, which leads us to style. Style ultimately is an aesthetic judgment. Did you choose good names for your variables? Have you indented your code properly? Does it look good, and therefore is it easy for another human being to read, irrespective of its correctness? Now, generally, per the syllabus, we score these things on a 5-point scale, and let me hammer home the point that a 3 is indeed good. Very quickly, do folks start doing arithmetic when they get a 3 out of 5 on correctness for some piece set, and they think, damn, I got a 60%, which is essentially a D or an E. That's not the way we think of these numbers. A 3 is indeed good, and what we generally expect at the beginning of the term is that if you're getting a bunch of 3s, maybe a couple fairs, a couple 4s, or a couple 2s, a couple 4s, that's a good place to start. And so long as we see an upward trajectory over time, you're in a particularly good place. The formula we use to weight things is essentially this per the syllabus, which just means that we give more weight to correctness, because it's very often correctness that takes the most time. Trust me now, you will find, at least in one piece set, that you spend 90% of your time working on 10% of the problem. And everything sort of works except for 1 or 2 bugs, and those are the bugs that keep you up late at night. Those are the ones that sort of escape you, but after sleeping on it a bit, attending office hours, or asking questions online, will you get to that 100% goal, and that's why we weight correctness the most. Design a little less, and style a little less than that. But keep in mind, style is perhaps the easiest of these to bite off, as per the style guide. And now a more serious note on academic honesty. CS50 has the unfortunate distinction of being the largest producer of ad board cases almost every year historically. This is not because students cheat in CS50 any more so than in any other class, but because by nature of the work, the fact that it's electronic, the fact that we look for it, and the fact that we're computer scientists, I can say we are unfortunately very good at detecting it. So what does this mean in real terms? So per the syllabus, the course's philosophy really does boil down to be reasonable. There is this line between doing one's work on your own and getting a little bit of reasonable help from a friend, and outright doing that work for your friend, or sending him or her your code so that he or she can simply take or borrow it outright. And that crosses the line that we draw in the class. See the syllabus ultimately for the lines that we draw as being reasonable and unreasonable behavior, but it really does boil down to the essence of your work needing to be your own in the end. Now, with that said, there is a heuristic, because as you might imagine from office hours and the visuals and the videos that we've shown thus far, CS50 is indeed meant to be as collaborative and as cooperative and as social as possible, as much as collaborative as it is rigorous. But with this said, the heuristic, as you'll see in the syllabus, is that when you're having some problem, you have some bug in your code that you can't solve, it is reasonable for you to show your code to someone else, a friend even in the class, a friend sitting next to you at office hours, or a member of the staff, but they may not show their code to you. In other words, an answer to your question, I need help, is not, oh, here's my code, take a look at this and deduce from it what you will. Now, of course, there's a way clearly to game this system whereby I'll show you my code before having a question, you show me your code before having a question, but see the syllabus again for the finer details of where this line is. Just to now paint a picture and share as transparently as possible where we are at in recent years. This is the number of ad board cases that CS50 has had over the past 7 years, with 14 cases this most recent fall. In terms of the students involved, it was 20 some odd students this past fall. There was a peak of 33 students some years ago, many of whom are unfortunately no longer here on campus. Students involved as a percentage of the class has historically ranged from 0% to 5.3%, which is only to say this is annually a challenge. And toward that end, what we want to do is convey, one, that we do, just FYI, compare out of fairness to those students who are following the line accordingly. We do compare all current submissions against all past submissions from the past many years. We know, too, how to Google around and find code repositories online, discussion forums online, job sites online. If a student can find it, we can surely find it as much as we regretfully do. So, what you'll see in the syllabus, though, is this regret clause. I can certainly appreciate, and we all as staff, having done a course like this or this one itself over time, certainly know what it's like when life gets in the way, when you have some late night deadline, not only in this class but another, when you're completely exhausted, stressed out, have an inordinate number of other things to do. You will make at some point in life certainly a bad, perhaps late night decision. So per the syllabus, there is this clause such that if within 72 hours of making some poor decision, you own up to it and reach out to me or one of the course's heads and we'll have a conversation, we will handle things internally in hopes of it becoming more of a teaching moment or life lesson and not something with particularly drastic ramifications, as you might see on these charts here. So that's a very serious tone. Let us pause for just a few seconds to break the tension. So how's that for a segue to today's primary topics, the first of which is abstraction, another of which is going to be the representation of data, which frankly is a really dry way of saying how can we go about solving problems and thinking about solving problems. So you've seen in Scratch, and you've seen perhaps already in PSET 1 with C, that you not only can use functions like printf that other people in years past wrote for you, you can also write your own functions. And even though you might not have done this in C, and frankly in PSET 1, you don't really need to write your own function because the problems, while perhaps daunting at first glance, you'll see can ultimately be solved with not all that many lines of code. But with that said, in terms of writing your own functions, realize that C does give you this capability. I'm going to go in today's source code, which is available already online, and I'm going to go ahead and open up a program called function0.c. And in function 0, we'll see a few things. In first, lines 18 through 23 is my main function. And now that we're beginning to read code, that we're not writing on the fly, but instead I've written in advance, or that you in a problem set might receive having been written in advance, a good way to start reading someone else's code is look for the main function. Figure out where that entry point is to running the program, and then follow it logically from there. So this program apparently prints your name, followed by a colon. We then use getString from the CS50 library to get a string, or a word or phrase from the user at the keyboard. And then there's this thing here, printName. Now, printName is not a function that comes with C. It's not in standard io.h. It's not in CS50.h. Rather, it's in this same file. Notice if I scroll down a bit, line 25 to 27 is just a pretty way of commenting your code using these stars and slashes. This is a multi-line comment, and this is just my description in blue of what this function does. Because in lines 28 through 31, I've written a super simple function whose name is printName. It takes how many arguments, would you say? So one argument, because there's one there's one argument listed inside of the parentheses, the type of which is string, which is to say printName is like this black box or function that takes as input a string. And the name of that string, conveniently, will be name. Not S, not N, but name. So what does printName do? It's nice and simple, just has one line of code with a printf, but apparently it prints out hello, comma, so-and-so, where the so-and-so comes from the argument. Now, this is not a huge innovation here. Really, I've taken a program that could have been written with one line of code by putting this up here and changed it to something that involves some 6 or 7 or so lines of code all the way down here. But it's a practicing of a principle known as abstraction, kind of encapsulating inside of a new function that has a name, and better yet, that name literally says what it does. I mean, printf, that's not particularly descriptive. If I want to create a puzzle piece, or if I want to create a function that prints someone's name, the beauty of doing this is that I can actually give that function a name that describes what it does. Now, it takes in an input that I've arbitrarily called name, but that too is wonderfully descriptive instead of being a little more generic like s. And void, for now, just means that this function doesn't hand me back anything. It's not like getString that literally hands me back a string, like we did with the pieces of paper with your classmates last week, but rather it just has a side effect. It prints something to the screen. So at the end of the day, if I do make function 0 / function 0, we'll see that it asks for my name. I type David, and it types out my name. If I do it again with Rob, it's going to say, hello, Rob. So a simple idea, but perhaps extrapolate from this mentally that as your programs get a little more complicated and you want to write a chunk of code and call that code, invoke that code by some descriptive name like print name, C does afford us this capability. Here's another simple example. For instance, if I open up a file from today called return.c, notice what I've done here. Most of this main function is printf. I first arbitrarily initialize a variable called x to the number 2. I then print out x is now %i, passing in the value of x. So I'm just saying what it is. Now I'm just boldly claiming with printf I am cubing that value x, and I'm doing so by calling a function called cube, passing in x as the argument, and then saving the output in the variable itself x. So I'm clobbering the value of x. I'm overwriting the value of x with whatever the result of calling this cube function is. And then I just print out some fluffy stuff here saying what I did. So what then is cube? Notice what's fundamentally different here. I've given the function a name as before. I've specified a name for an argument. This time it's called n instead of name, but I could call it anything I want. But this is different. This thing on the left. Previously it was what keyword? Void. Now it's obviously int. So what's perhaps the takeaway? Whereas void signifies sort of nothingness, and that was the case. Print name returned nothing. It did something, but it didn't hand me back something that I could put on the left-hand side of an equal sign, like I've done here on line 22. So if I say int on line 30, what's that probably implying about what cube does for me? Yeah? It returns an integer, so it hands me back, for instance, a piece of paper on which is written the answer. 2 cubed, or 3 cubed, or 4 cubed, whatever I've passed in. And how did I implement this? Well, just n times n times n is how I might cube a value. So again, super simple idea, but demonstrative now of how we can write functions that actually hand us back values that might be of interest. Let's look at one last example here called function 1. In this example, it starts to get more compelling. So in function 1, this program, notice, ultimately calls a function called getPositiveInt. GetPositiveInt is not a function in the CS50 library, but we decided we would like it to exist. So if we scroll down later in the file, notice how I went about implementing getPositiveInt. And I say it's more compelling because, all right, this is a decent number of lines of code. It's not just a silly little toy program. It's actually got some error checking and doing something more useful. So if you've not seen the walkthrough videos that we have embedded in PSET 1, know that this is a type of loop in C, similar in spirit to the kinds of things Scratch can do. And do says, do this, print this out, then go ahead and get n, get an int and store it in n, and keep doing this again and again and again so long as n is less than 1. So n is going to be less than 1 only if the human's not cooperating. If he or she is typing in 0 or -1 or -50, this loop is going to keep executing again and again. And ultimately, notice, I simply return the value. So now we have a function that would have been nice if CS50 had implemented in CS50.h and CS50.c for you, but here we can now implement this ourselves. But 2 comments on some key details. 1, why did I declare int n, do you think, on line 29, instead of just doing this here, which is more consistent with what we did last week? Yeah? It's a good thought. So if we were to put it here, it's as though we keep declaring it again and again. That in and of itself is not problematic per se, because we only need the value once, and then we're going to get a new one anyway. But a good thought, yeah?
If you
Close. So whereas, because I've declared n on line 29 outside of the loop, it's accessible throughout this entire function, not to other functions, because n is still inside of these curly braces here. So the issue, sure. Exactly. So this is even more to the point. If we instead declared n right here on line 32, it's problematic because guess where else I need to access it? On line 34. And the simple rule of thumb is that you can only use a variable inside of the most recent curly braces in which you declared it. Unfortunately, line 34 is one line too late because I've already closed the curly brace on line 33 that corresponds to the curly brace on line 30. And so this is a way of saying that this variable n is scoped, so to speak, to only inside of those curly braces. It just doesn't exist outside of them. So indeed, if I do this wrong, let me save the code as it is, incorrectly written. Let me go ahead and do make function -1, and notice error, use of undeclared identifier n on line 35, right, which is right here. And if we scroll up further, another one, use of undeclared identifier n on line 34. So the compiler, Clang, is noticing that it just doesn't exist, even though clearly it's there visually, so a simple fix is declaring it there. Now let me scroll up to the top of the file. What jumps out at you as being a little different from the stuff we looked at last week? Not only do I have main, not only do I have some sharp includes up top, I have something I'm calling a prototype. Now that looks awfully similar to what we just saw a moment ago on line 27. So let's infer from a different error message why I've done this. Let me go ahead and delete these lines there, as though we know nothing about prototypes, remake this file, make function 1, and now, damn, 4 errors. Let's scroll up to the first one. Implicit declaration of function getPositiveInt is invalid in C99. C99 just means the 1999 version of the language C, which is what we're indeed using. So what does this mean? Well, C, and more specifically, C compilers are pretty dumb programs. They only know what you've told them, and that's actually thematic from last week. The problem is that if I go about implementing main up here, and I call a function called getPositiveInt here on line 20, that function technically doesn't exist until the compiler sees line 27. Unfortunately, the compiler is doing things top down, left, right, so because it has not seen the implementation of getPositiveInt, but it sees you trying to use it up here, it's just going to bail, yell at you with an error message, perhaps cryptic, and not actually compile the file. So a so-called prototype up here is admittedly redundant. Literally, I went down here and I copied and pasted this, and I put it up here. Void would be more proper, so we'll literally copy and paste it this time. I literally copied and pasted it, really just as like a breadcrumb, a little clue to the compiler. I don't know what this does yet, but I'm promising to you that it will exist eventually. And that's why this line in line 16 ends with a semicolon. It is redundant by design. Yeah? If you didn't link your library to the bottom. Oh, good question. Sharp includes, header file inclusions, should almost always be at the very top of the file for exactly the same reason, yes. Because in standard.io.h is literally a line like this, but with the word printf and with its arguments and its return type. And so by doing sharp include up here, what you're literally doing is copying and pasting the contents that someone else wrote up top, thereby cluing your code into the fact that those functions do exist. Yeah? Absolutely. So a very clever and correct solution would be, you know what, I don't know what a prototype is, but I know if I understand that C is just dumb and reads things top to bottom, well, let's give it what it wants. Let's cut that code, paste it up top, and now push main down below. This, too, would solve the problem. But you could very easily come up with a scenario in which sort of A needs to call B, and maybe B calls back to A. It's something called recursion, and we'll come back to that. And it may or may not be a good thing, but you can definitely break this solution. And moreover, I would claim stylistically, especially when your programs become this long, it's just super convenient to put main at the top, because it's the thing most programmers are going to care about. And so it's a little cleaner, arguably, to do it the way I originally did it, with a prototype, even though it looks a little redundant at first glance. Yeah? Sorry, can you say it louder? If you switch the locations of the implementation and the prototype? So that's a good question. If you redeclare this down here, let's see what happens. So if I put this down here, you're saying? Oh, sorry, louder? Even louder. Oh, good question. Would it invalidate the function? You know, after all these years, I have never put a prototype afterwards. So let's do make function 1. After doing that, get valid. Oh, wait, we still have to put everything up top. So let's do this up here. If I'm understanding your question correctly, I'm putting everything, including the prototype, above main, but I'm putting the prototype below the implementation. So if I make 1, I'm getting back an error, unused variable n. Oh, there, thank you. Let's see, we get rid of this. That's a different bug, so let's ignore that. Let's really quickly remake this. Okay, so data argument not used by format string, and oh, that's because I changed these here. All right, we know what the answer is going to. Here we go. Thanks for the positive. All right, I will fix this code after. Ignore this particular bug since this was a. It works, is the answer. So it doesn't overwrite what you've just done. I suspect the compiler is written in such a way that it is ignoring your prototype because the body, so to speak, of the function has already been implemented higher up. I would have to actually consult the manual of the compiler to understand if there's any other implication, but at first glance, just by trying and experimenting, there seems to be no impact. Good question. All right, so let's forge ahead now, moving away from side effects, which are functions that do something, like visually on the screen with printf, but don't return a value, and functions that have return values, like we just saw a few of. We already saw this notion of scope, and we'll see this again and again, but for now, again, use the rule of thumb that a variable can only be used inside of the most recently opened and closed curly braces, as we saw in that particular example. And as you pointed out, there is an ability. You could solve some of these problems by putting a variable globally at the very top of a file, but in almost all cases will we frown upon that and indeed not even go into that solution for now. So for now, the takeaway is that variables have this notion of scope. But now let's look at another dry way of actually looking at some pretty interesting implementation details, how we might represent information. And we already looked at this in the first week of the class, looking at binary and reminding ourselves of decimal. But recall from last week that C has different data types, and bunches more, but the most useful ones for now might be these. A char, or character, which happens to be 1 byte, or 8 bits total, and that's to say that the size of a char is just 1 byte. A byte is 8 bits, so this means that we can represent how many characters, how many letters or symbols on a keyboard if we have 1 byte or 8 bits. Think back to week 0. If you have 8 bits, how many total values can you represent with patterns of zeros and ones? Even more than that. So 256 total, if you start counting from 0. So if you have 8 bits, so if we had our binary bulbs up here again, we could turn those light bulbs on and off in any of 256 unique patterns. Now, this is a bit problematic, not so much for English and Romance languages, but certainly when you introduce, for instance, Asian languages, which have far more symbols than like 26 letters of the alphabet, we actually might need more than 1 byte. And thankfully, in recent years, has society adopted other standards that use more than 1 byte for chars. But for now, in C, the default is just 1 byte or 8 bits. In integer, meanwhile, is 4 bytes, otherwise known as 32 bits, which means what's the largest possible number we can represent with an int, apparently?
Something like a billion.
So with a billion, so it's 4 billion, give or take. 2 to the 32th power, if we assume no negative numbers and just use all positive numbers, it's 4 billion, give or take, possibilities. A float, meanwhile, is a different type of data type in C. It's still a number, but it's a real number, something with a decimal point, and it turns out that C also uses 4 bytes to represent floating point values. Unfortunately, how many floating point values are there in the world? How many real numbers are there? So it's an infinite number, right? And for that matter, there's an infinite number of integers. So we're already kind of digging ourselves a hole here, whereby apparently in computers, at least programs written in C on them, can only count as high as 4 billion, give or take, and floating point values can only apparently have some finite amount of precision, only so many digits after their decimal point, because of course, if you only have 32 bits, I don't know how we're going to go about representing real numbers, probably with different types of patterns, but there's surely a finite number of such patterns. So here, too, this is problematic. Now, we can kind of avoid the problem slightly. If you don't use a float, you can use a double in C, which gives you 8 bytes, which is way more possible patterns of zeros and ones, but it's still finite, which is going to be problematic if you ever write software for graphics or for fancy mathematical formulas where you might actually want to count up bigger than that. A long, stupidly named, is also 8 bytes, or 64 bits, and this is twice as long as an int, and it's for a long integer value. Fun fact, if an int is 4 bytes, how long is a long in C, typically? Also 4 bytes, but a long is 8 bytes, and this is for historical reasons. But the takeaway now is just that data has to be represented in a computer that's a physical device with electricity generally driving those zeros and ones with finite amounts of precision. So what's the problem then? Well, there's the problem of integer overflow, not just in C, but in computers in general. For instance, if this is a byte's worth of bits, so if this is 8 bits, all of which are the number 1, what number is this representing if we assume it's all positive values in binary? 255. And it's not 256 because 0 is the lowest number, so 255 is the highest one. But the problem is, suppose that I wanted to increment this variable that is using 8 bits total if I want to increment it. Well, as soon as I add a 1 to all of these 1s, you can perhaps imagine visually, just like carrying the 1 using decimal, something's going to kind of flow to the left. And indeed, if I add the number 1 to this, what happens in binary is that it overflows back to 0. So if you only use, not an int, but a single byte to count integers in a program, by default, as soon as you get to 250, 251, 252, 253, 254, 255, 0 comes after 255, which is probably not what a user is going to expect. Now, meanwhile, in floating point worlds, you also have a similar problem, not so much with the largest number, although that's still an issue, but with the amount of precision you can represent. So let's take a look at this example here, also from today's source code, floats0.c. And notice a super simple program that should apparently print out what value? What do you wager this is going to print, even though there's a bit of new syntax here? So hopefully 0.1, so the equivalent of 1/10, because I'm doing 1 divided by 10. I'm storing the answer in a variable called f. That variable's of type float, which is a keyword I just proposed existed. And we've not seen this before, but this is kind of a neat way in printf to specify how many digits you want to see after a decimal point. So this notation just means here's a placeholder. It's for a floating point value. And oh, by the way, show it with a decimal point with 1 number after the decimal point. So that's the number of significant digits, so to speak, that you might want. So let me go ahead and do make floats0 / floats0. And apparently 1 divided by 10 is 0.0. Now, why is this? Well, again, the computer's taking me literally. And I have written 1 and I have written 10. And take a guess, what is the assumed data type for those two values? So an int. It's technically something a little different. It's typically a long, but it's ultimately an integral value, not a floating point value. Which is to say that if this is an int and this is an int, the problem is that the computer doesn't have the ability to even store that decimal point. So when you do 1 divided by 10 using integers for both the numerator and the denominator, the answer should be 0.1. But the computer, because you're using because those are integers, doesn't know what to do with the 0.1, so what is it clearly doing? It's just throwing it away. And what I'm seeing ultimately is 0.0 only because I insisted that printf show me 1 decimal point. But the problem is that if you divide an integer by an integer, you will get, by definition of C, an integer. And it's not going to do something nice and convenient like round it up to the nearest 1 up or down. It's going to truncate everything after the decimal. So just intuitively, what's probably a fix? What's the simplest fix here? Yeah? Exactly. Why don't we just treat these as floating point values, effectively turning them into floats or doubles, and now if I do make floats 0, or if I compile floats 1, which is identical to what was just proposed, and now I do floats 0, now I get my 0.1. Now this is amazing, but now I'm going to do something a little different. I'm curious to see what's really going on underneath the hood, and I'm going to print this out to 28 decimal places. I want to really see 0.10000, an infinite, 27 zeros after that 0.1. Well, let's see if that's what I indeed get. Make floats 2, whoops, yeah, make floats 0, same file, / floats 0. Let's zoom in on the dramatic answer. All this time, you've been thinking 1 divided by 10 is 10%, or 0.1. It's not, at least so far as the computer is concerned. Now, why? Okay, that's a complete lie. So 1 divided by 10 is 0.1. But why? That is not the takeaway today. So why does the computer think, unlike all of us in the room, that 1 divided by 10 is actually that crazy value? What's the computer doing, apparently? What's that? Oh, it's not overflow per se. Overflow is typically when you wrap around a value. It's this issue of imprecision. In a floating point value, you only have 32 or maybe even 64 bits. But if there's an infinite number of real numbers, numbers with decimal points and numbers thereafter, surely you can't represent all of them. So the computer has given us the closest match to the value it can represent using that many bits to the value I actually want, which is 0.1. Unfortunately, if you start doing math or you start involving these kinds of floating point values in important programs, financial software, military software, anything where precision is probably pretty important, and you start adding numbers like this and start running that software with really large inputs or for lots of hours or lots of days or lots of years, these tiny little mistakes surely can add up over time. Now, as an aside, if you've ever seen Superman 3 or Office Space, and you might recall how those guys stole a lot of money from their computer by using floating point values and adding up the little remainders, hopefully that movie now makes more sense. This is what they were alluding to in that movie, the fact that most companies wouldn't look after a certain number of decimal places, but those are fractions of cents. So you start adding them up, and you start to make a lot of money in your bank account. So that's Office Space explained. Now, unfortunately, beyond Office Space, there are some legitimately troubling and significant impacts of these kinds of underlying design decisions. And indeed, one of the reasons we use C in the course is so that you really have this ground-up understanding of how computers work, how software works, and don't take anything for granted. And indeed, unfortunately, even with that fundamental understanding, we humans make mistakes. And what I thought I'd share is this 8-minute video here, taken from a Modern Marvels episode, which is a educational show on how things work, that paints 2 pictures of when an improper use and understanding of floating point values led to some significant, unfortunate results. Let's take a look.
We now return to engineering disasters on Modern Marvels. Computers. We've all come to accept the often frustrating problems that go with them. Bugs, viruses, and software glitches are small prices to pay for the convenience. But in high-tech and high-speed military and space program applications, the smallest problem can be magnified into disaster. On June 4th, 1996, scientists prepared to launch an unmanned Ariane 5 rocket. It was carrying scientific satellites designed to establish precisely how the Earth's magnetic field interacts with solar winds. The rocket was built for the European Space Agency and lifted off from its facility on the coast of French Guiana.
At about 37 seconds into the flight, they first noticed something was going wrong, that the nozzles were swiveling in a way they really shouldn't. Around 40 seconds into the flight, clearly the vehicle was in trouble, and that's when they made a decision to destroy it. The range safety officer, with tremendous guts, pressed the button, blew up the rocket before it could become a hazard to public safety.
This was the maiden voyage of the Ariane 5, and its destruction took place because of a flaw embedded in the rocket's software.
The problem on the Ariane was that there was a number that required 64 bits to express, and they wanted to convert it to a 16-bit number. They assumed that the number was never going to be very big, that most of those digits in the 64-bit number were zeros. They were wrong.
The inability of one software program to accept the kind of number generated by another was at the root of the failure. Software development had become a very costly part of new technology. The Ariane 4 rocket had been very successful, so much of the software created for it was also used in the Ariane 5.
The basic problem was that the Ariane 5 was faster, accelerated faster, and the software hadn't accounted for that.
The destruction of the rocket was a huge financial disaster, all due to a minute software error. But this wasn't the first time data conversion problems had plagued modern rocket technology.
In 1991, with the start of the first Gulf War, the Patriot missile experienced a similar kind of number conversion problem. And as a result, 28 people, 28 American soldiers were killed and about 100 others wounded when the Patriot, which was supposed to protect against incoming Scuds, failed to fire a missile.
When Iraq invaded Kuwait and America launched Desert Storm in early 1991, Patriot missile batteries were deployed to protect Saudi Arabia and Israel from Iraqi Scud missile attacks. The Patriot is a U.S. medium-range surface-to-air system manufactured by the Raytheon Company.
The size of the Patriot interceptor itself it's about roughly 20 feet long, and it weighs about 2,000 pounds. And it carries a warhead of about, I think it's roughly 150 pounds. And the warhead itself is a high explosive, which has fragments around it. The casing of the warhead is designed to act like buckshot.
The missiles are carried 4 per container and are transported by a semi-trailer.
The Patriot anti-missile system goes back at least 20 years now. It was originally designed as an air defense missile to shoot down enemy airplanes. In the first Gulf War, when that war came along, the Army wanted to use it to shoot down Scuds, not airplanes. The Iraqi Air Force was not so much of a problem, but the Army was worried about Scuds. And so they tried to upgrade the Patriot.
Intercepting an enemy missile traveling at Mach 5 was going to be challenging enough. But when the Patriot was rushed into service, the Army was not aware of an Iraqi modification that made their Scuds nearly impossible to hit.
What happened is the Scuds that were coming in were unstable. They were wobbling. The reason for this was the Iraqis, in order to get 600 kilometers out of a 300-kilometer range missile, took weight out of the front warhead. They made the warhead lighter. So now the Patriot's trying to come at the Scud, and most of the time, the overwhelming majority of the time, it would just fly by the Scud.
Once the Patriot system operators realized the Patriot missed its target, they detonated the Patriot's warhead to avoid possible casualties if it was allowed to fall to the ground.
That was what most people saw as big fireballs in the sky and misunderstood as intercepts of Scud warheads.
Although in the night skies, Patriots appeared to be successfully destroying Scuds, at Daharan, there could be no mistake about its performance. There, the Patriots' radar system lost track of an incoming Scud and never launched due to a software flaw. It was the Israelis who first discovered that the longer the system was on, the greater the time discrepancy became, due to a clock embedded in the system's computer.
About 2 weeks before the tragedy in Bahrain, the Israelis reported to the Defense Department that the system was losing time. After about 8 hours of running, they noticed that the system was becoming noticeably less accurate. The Defense Department responded by telling all of the Patriot batteries to not leave the systems on for a long time. They never said what a long time was. 8 hours, 10 hours, 1,000 hours. Nobody knew.
The Patriot battery stationed at the barracks at Daharan and its flawed internal clock had been on over 100 hours on the night of February 25th.
It tracked time to an accuracy of about 1/10 of a second. Now, 1/10 of a second is an interesting number because it can't be expressed in binary exactly, which means it can't be expressed exactly in any modern digital computer. It's hard to believe, but use this as an example. Let's take the number 1/3. 1/3 cannot be expressed in decimal exactly. 1/3 is 0.333 going on for infinity. There's no way to do that with absolute accuracy in decimal. That's exactly the same kind of problem that happened in the Patriot. The longer the system ran, the worse the time error became.
After 100 hours of operation, the error in time was only about 1/3 of a second. But in terms of targeting a missile traveling at Mach 5, it resulted in a tracking error of over 600 meters. It would be a fatal error for the soldiers at Daharan.
What happened is a a Scud launch was detected by early warning satellites, and they knew that the Scud was coming in their general direction. They didn't know where it was coming.
It was now up to the radar component of the Patriot system, defending Daharan, to locate and keep track of the incoming enemy missile.
The radar was very smart. It would actually track the position of the Scud and then predict where it probably would be the next time the radar sent a pulse out. That was called the range gate.
Then, once the Patriot decides enough time has passed to go back and check the next location for this detected object, it goes back. So when it went back to the wrong place, it then sees no object, and it decides that there was no object, it was a false detection, and drops the track.
The incoming Scud disappeared from the radar screen, and seconds later, it slammed into the barracks. The Scud killed 28, and was the last one fired during the First Gulf War. Tragically, the updated software arrived at Daharan the following day. The software flaw had been fixed, closing one chapter in the troubled history of the Patriot missile.
That's it for CS50. We will see you on Wednesday.